So hello everyone and welcome back. As usual, we have a couple of minutes before class officially starts. If anyone has questions, they can ask them in the chat window. And while I wait for that, I will make an announcement because I've been watching some of the chatter on Discord about assignments. And I think many of you maybe were disheartened after assignment 3 because it seemed harder than the rest. So a couple of things about that. One is, so I've collected the marks for assignment 3 now. And among those who didn't get 0, the average mark was about 66%, so that's about a C, which is not super high, but not terrible either. But that's not the point. I think the main point is, of course, we're in a strange time now, in which we've changed a lot of things up, and one of the things that we changed up for this course is the overall grading scheme. So exams are not worth terribly much, and all of your weight is basically on all of the marks are basically on assignments, or at least 75% of it. So that has a consequence, which is that we cannot have everybody get 100% on every assignment, right? Our job, of course, is to educate you, but it is also to give some distinction to people who know the material exceptionally well. And usually that's done because those people do really well on exams. But of course, there are problems with exams in the current environment, so we don't want to rely on that. So all that to say, if you're used to getting 100% on assignments or fully completing assignments and feeling like you did really well, and that didn't happen with assignment 3, don't feel bad about yourself, and don't feel bad that happened. In the same way that you wouldn't feel bad if you wrote an exam and you didn't get 100%. And I think most of the time when we write exams, we don't get 100%. So some of the questions in assignment 3 were designed to be very difficult, so that the people with the greatest understanding and who put in the greatest effort will be the only ones who get full marks for that. All that just to say, don't feel too badly about yourselves. If you didn't get 100%, very few people did. Okay, any questions? For assignment 4, are we allowed to create other classes? Yes. You can create other classes. Please put them in the COMP2402 A4 package, just to avoid conflicts with other files that might show up. That's fine. The server will compile all of the Java files that it finds in that directory, so that should be okay. No, the server does not delete everything automatically. Okay, so other question is, would I say that A4 is relatively easier? Assignment 4 is different. So I think for the first 3 assignments, it was the choices were relatively clear. So there were specific problems to solve, and there was kind of generally the path to the right one, if you understood what was going on, the path to the solution was fairly clear. Like in assignment 1, it's basically about picking the right data structure to use. And then in assignment 2 and 3, you're given implementations that are sort of partially completed, and even given hints about what you should do to fully complete them. For assignment 4, it's a bit more open-ended. We really have just given you the description of the interface, and it's your job to put together the ideas that you've seen in this course in order to implement all of those operations in the interface as efficiently as possible. So I think there will be a bit more work up front thinking about your solutions before you just jump in and start hacking away. So you want to think through what the data structure is that you want to implement. And once you've done that, then actually the coding is quite a bit, the actual coding is quite a bit simpler than in assignment 3. Yes, assignment 4 is up. Was put up yesterday. I posted it on the course forum, an announcement, but CU Learn was acting strange when I did that. So I basically hit submit, and CU Learn hung on me. And a half hour later, when I was able to get back into CU Learn, the announcement was posted. So it wasn't clear to me whether you guys received any notification of that or not. But assignment 4 is available now. And you have as much time to complete it as I'm allowed to give you. So it's due on the last day of classes. Okay, so today we're going to talk about sorting. And actually, what may be a little bit surprising is much of this will be review, because these are things that we've already done, although you may not have recognized them as sortings. But we're going to look at sorting algorithms. So the first sorting algorithm I want to look at is one that we somehow didn't show up in any of the data structures that we studied, but it's a real classic. It's called the Mergesort algorithm. And actually, this is probably not the first occurrence of it, but it shows up in a 1938 US patent for a sorting machine that was sorted punch cards based on the dots in them. It was later invented, 7 years later, sort of as a computer algorithm by John von Neumann. And it's probably not even the first discovery, just the most famous discoverer. And the algorithm works as follows. So you have an array that contains values a0 up to an minus 1, so an array of length n. And the first thing you do is you sort the first half of the array. So recursively sort the first half of the array. Then you recursively sort the second half of the array. So the first half is at positions 0 up to n over 2, and the second half is at positions n over 2 plus 1 up to n minus 1. And then you merge the two sorted sequences. So you've sorted the first half, you've sorted the second half, then you merge those two sorted sequences. So looks like this. So in this picture, you imagine taking your input array and splitting it into two. So here it's showing you the input list of numbers, 93521876064. And then there's the first half, which goes from 9 up to the 1, and the second half, which goes from 8 up to 4. Sort the first half, that turns that into 12359. Sort the second half, that turns that into 04678. And then you use a fairly easy linear time algorithm that merges those two sorted sequences. And I think most of you have seen this before. If you've been in, we've done it in COMP2402 already. or you may have come across it somewhere else. And in COMP2402 we even analyzed it. Here's what it looks like in Java. It's not particularly difficult. The only sort of issue is you need some extra space somewhere. And in this particular application, that you get that by copying the first half of the array into a new array called A0 and copying the second half of the array into a new array called A1. Then you recursively merge sort A0 and you recursively merge sort A1, and then you call this merge function. And of course, although the Siri's talking to me, I'm not okay. Goodbye, Siri. Then you recursively sort the first and second halves, and then you merge these two things. And so what's really happening here is A0 is an array, A1 is an array, and now whatever you get when you merge that, you're copying all of that back into the original input array A. Okay. So there's really a whole second copy of all your data. And of course, the one thing that I skipped when we just presented this in bullet form is the base case. So if the length of the array is less than or equal to 1, then there's nothing to do. An array of length 0 or an array of length 1 is already sorted. And the merge function is a little bit longer, but not particularly difficult. It maintains basically two indices, one into A0, one into A1, and it just keeps looking at, so those start at the beginning of A0 and A1, and it keeps comparing the two elements that those point to, and whichever one is the smaller of those two will be the next one to go into the array A. Until you run out of, one of them runs out of elements, and then the rest go in there. So that's all this code is doing. There's a for loop. At each iteration of the for loop, another element gets added to the sorted array A, and there's 4 cases that decide whether it comes from A0 or A1. Okay, so the merge algorithm, that's easy to see that it takes order n time. There's a for loop with some if statements inside it, and the for loop runs for n iterations, or the length of the array A. So that's easy to see. But the whole algorithm, the whole merge sort algorithm, remember it's recursive, so to analyze it, you have to solve some kind of recurrence. And here's how it works. So let's say T of n is the time it takes to run merge sort on an array of length n. Let's just define that. And we want to know a closed form for T of n. Well, you do the first step, and what's the first step? The first step is to sort an array of length n over 2, the first half of the array. And so by the definition, that means that takes T of n over 2 time. The second step involves sorting the second half, which is another array of length T of n over 2. So by definition, that takes T of n over 2 time. And we already argued that the merge step takes O of n time. So you get a running time recurrence that looks like this. So T of n is O of n time for the merging and also for the copying into the two subarrays A0 and A1. And then you have 2 recursive calls, each on a problem of size n over 2. And you can solve this by induction, or you can just expand it until you see what's happening. So if I start with this original recurrence, I can expand the T of n over 2 here just by applying the same thing again, right? So T of n over 2 is O of n over 2 plus 2 T of n over 4, but all that is multiplied by 2. And so what's left, there's still this thing here that we haven't expanded yet, but we can expand it again. Well, so before that, 2 O of n over 2 is, I'll abuse the notation a bit and say that's just O of n. And then we can expand this thing. And we do that again, so that's 4 O of n over 4 plus 8 t of n over 8, right? So there was the t of n over 4 is O of n over 4 plus 2 t of n over 8, but both of those things are multiplied by 4. And if you just keep doing this, you realize that at each level of this expansion, you're getting another O of n term until eventually you get down to these problems of size 1. So you'll get down to t of 1, and you have n problems of size 1. And how many terms are there? Well, there's one of these came from an O of n. This was 2 O of n over 2s. This was 4 O of n over 4s. And so that means that so at each time the size of the subproblem is getting smaller by a factor of 2, but the number of subproblems is doubling. But how many steps does this take until the size of the subproblem becomes 1? Well, that's exactly log n, right? So the number of times I can divide n by 2 before I get something less than or equal to 1 is our working definition of log n. So this all works out to O of n log n. So that's the result for Mergesort. It's a n log n time sorting algorithm. And if you look at this a little bit more carefully, and you don't use big O notation, instead if you carefully count where the comparisons are happening, or how many comparisons are happening, the only time elements get compared, so comparisons are between things in the array, the only time elements get compared is during the merge procedure. And the merge procedure does, in fact, it does at most n minus 1 comparisons, but that's certainly at most n comparisons. And so if you work it out more carefully, you'll see that it runs in O of n log n time, which we already discussed, but the number of comparisons is at most n log n. Okay. So, and for a lot of times when we study sorting, somehow this number of comparisons is really the critical thing that we're interested in, although we'll see soon enough that that's not doesn't tell the whole story. Okay, so that's Mergesort. Now back to something that I will say is a review, although you may not have recognized it. Quicksort. So Quicksort, if you remember, or if you don't remember, it doesn't matter. Quicksort takes an array of elements, and the first thing it does is it picks a random index in that array. So in this case, it looks like it picked 9 as its random index. And can I explain the at most n log n? So someone wants to, I'll back up, wants to know about this at most n log n comparisons here. Yeah, so that just comes from, we have this recurrence which was about the running time, but instead if I say let's make this recurrence be about something more specific than the running time, let's say it wants to count the number of comparisons, then the comparisons only happen in the merge procedure. And the number of comparisons that happen in the merge procedure is at most n. Okay. So, so everywhere you see O of n in this derivation here, and you don't want equals anymore, if you want less than or equals, replace each of those O of n's with just an n. And if you do that, then you'll see that you get you really get n log n, not O of n log n. Because if we back up and just look at the even at the code, notice that in this part of the algorithm, there's no comparisons. Some data gets copied, but no elements ever get compared. The only comparisons that happen are in the merge function, where we do a comparison here. We compare two elements, one from A0 and one from A1, and this is inside of a loop that executes n times. So this happens at most n times. Okay. So we'll just keep this in mind, that the number of comparisons by Mergesort is at most n log n, and this is log base 2 of n, and there's no constant hiding there. It's 1 times n log n. Okay, so back to Quicksort. Quicksort picks a random element from the array, and then it partitions the array into a bunch of things which are all smaller than that element, and a bunch of things which are all larger than that element. So that's what's called the pivot part of Quicksort that does this partitioning. So it compares everything to this randomly chosen element and decides it should go before it, or it decides it should go after it. In case there's ties, then you get a bunch of equal ones in the middle, but to make our lives easy, let's assume everything is distinct. All right, so that does that pivot routine, and then what's left to do is to sort all the stuff that is smaller than the pivot, and so that's a recursive call to Quicksort, and then sort all of the stuff which is larger than the pivot. That's another recursive call to Quicksort. And so I claim that we have seen this algorithm before, and we've seen that its running time is O of n log n, and it does at most, so it's a randomized algorithm because it makes this random choice of pivot, but the expected number of comparisons is this 1.38 n log n. And to explain that, let me just go back to the board. So the thing that we've seen that looks, where we've seen Quicksort before is when we studied random binary search trees. So when we studied random binary search trees, we said, well, you have a random permutation of n distinct values, and you insert them one at a time into a binary search tree. So if these are my n distinct values, then the first thing in a random permutation is just a random choice from these n values, right? So the first thing in the random permutation is some random choice x, and in a random binary search tree, we then insert x into an empty tree. So it's the root of, it just becomes the root of this tree. And then we go ahead and we walk through the permutation and keep inserting things. Now, when we do that, what's going to happen is every element that we insert after this is going to get compared to x. And those that are smaller are going to go off into this side, and those that are larger are going to go off into this side. Now, if you think about it, you'll realize, oh, that is exactly the same comparisons that Quicksort does, right? Quicksort chooses X and then compares everything to X and decides whether it's going to go on the left or the right. A random binary search tree, you can imagine it chooses X, and then eventually everybody will have to get compared with X. It'll happen a little bit later, but it'll be exactly the same things. Everybody who's compared with X in the Quicksort execution will also be compared with X in the random binary search tree. And we saw this theorem about random binary search trees, which says that the expected length of a search path for any element is this 2n times the natural logarithm of n, which when you translate this into a binary logarithm, you get roughly 1.38. So the expected length of a search path is 2 times the natural logarithm of n. You translate to a binary logarithm, you get 1.38. The binary log of n, and there's n things in your tree, so you get 1.38 n log n. So Quicksort is really nothing more than an efficient and compact way of doing what you do when you build a random binary search tree, but without actually building the tree. Instead of building it, you end up with the final result, which is all the data sorted in an array. Okay, so we've studied this already, and we know what it looks like. The only thing that we didn't cover, and I won't bother, is this routine, this pivoting routine that partitions into the stuff smaller than the pivot and the stuff larger than the pivot. It's kind of an exercise to show that you can do that without an extra array. So you can use the original array A that you started with, and by carefully, you maintain 3 indices into A, and by shuffling things carefully, everything gets compared to 9, and at the end of the process, you finish in this state, this sorted, not sorted, but this partitioned state, without using an extra array. Okay. What if the last element was chosen as pivot? Would that mean O of n complexity? Well, the point is, it's always a random element chosen as a pivot, and so even if in the first step you choose the last element as the pivot, so the largest value as the pivot, like here, 13. That means that, yes, then you'll be recursing on all of this, and then there's nothing to the right. But that recursion, again, is going to choose a random element, and that's not likely to be the largest element again, right? So we only get we get an expected running time, and it's the same in the same way that in a random binary search tree. Right, so a random permutation could, by chance, start with the largest element in your set, in which case that becomes the root of the random binary search tree, and everything else has to go in the left subtree. But the on average, or the expected number of comparisons is still this, at most 1.38 n log n. Okay, so that's, if you're really looking at the number of comparisons, that's not as good as Mergesort. There's this 1.38 instead of a 1. On the other hand, this doesn't need an extra array. Okay, so everything, all the movement of data takes place inside the original array, and in some settings that's useful if you're trying to save space, or if you just are trying to make something that's very reliable. Because with Mergesort, for example, if you try and allocate an extra array and that memory is just not available, then what do? Does the algorithm give up and fail? That's not good in a reliable system, or things like embedded systems. And so it's an advantage that this is what's called an in-place algorithm that doesn't need an extra array. It sorts everything in the same array that it came in. Okay, and the third kind of sorting algorithm that we've seen, and I mentioned this one definitely explicitly when we were talking about binary heaps, is what's called the Heapsort algorithm. And there we saw that, all right, we have a binary heap which can be implemented as an array, even though we think of it as a binary tree. It packs neatly into an array using this Eitzinger layout. And if you give me an array with all the stuff in it, I can actually turn it into a binary heap fairly quickly. We went over that quickly. There's a bottom-up routine that can do that using in O of n time. And then after that, all you do is, right, so the whole point of heaps is that you can remove the min element, or if you invert the order, you can remove the max element, but the min element, let's say. And when you do that, what do you replace the min element with? Well, you take the last element in the heap and you put it where the min is that you just took out, and then you do some fixing up to make sure that it's a heap again. The point is, if I want to do sorting, I can take the min element, which is stored at position 0, the root of the heap, and swap it with the last element in the heap. Okay. Now the first n-1 elements of my array, and do the thing that I usually do with a heap. So now the first n-1 elements of my array are a heap, and the last element is the smallest element in my set. And if I do that again, then the first n-2 elements of my array are a heap, and the second last element is the second smallest. So I can keep doing this, and so at any point in time, there's a first part of the array which is a heap on all of the stuff that I haven't finished with yet, and the second part of the array is the stuff sorted, the array elements in sorted order, in this case in reverse sorted order, but you can change you can just negate the result of comparison, so make a max heap instead of a min heap, and get them in perfect sorted order, or if you don't even want to do that, get them in reverse sorted order, and then reversing an array is really trivial, right? You just have to swap the first and last element, the second and second last, and so on. And those heap operations, they run in log n time per operation, and you have to do n of them, so you get O of n log n time. And that's worst case. There's nothing randomized about it. And if you count the number of comparisons carefully, you'll see that it's at most 2n log n. So why 2? Well, that comes from the heap, the reheaping algorithm. So if you look at this picture, for example, the next step would be to take 5 and swap it with 12, so that 5 is in the right place in the sorted part of the array, and then 12 becomes the root of the heap. Now that's not a valid heap, because the smallest thing is supposed to be at the root of the heap, And the way we fix that is we would look at the root, which is 12 now after we've done this swap, and its two children, and we find the smallest of those three things, and that becomes the root. And finding the smallest out of three things takes two comparisons. Right? So if I want to know what's the minimum of three values, A, B, and C, well, I compare A and B. The smaller of those is still a candidate, but I still have to check it against C. So it takes two comparisons to find the minimum of three things, and that's what you have to repeatedly do when you're fixing a heap after you've put something at the root that's maybe too big. So that's where this 2 comes from. Okay. So that's 3 sorting algorithms. Quicksort runs in n log n expected time, Heapsort in n log n time, and Mergesort in n log n time. Quicksort is nice because it does everything in the array that you give it, so it's an in-place algorithm. Heapsort also has that property, so it's nice for that reason. And Mergesort, Mergesort doesn't have that property, but if I look at the number of comparisons, Quicksort has this 1.38 n log n, but it's only expected. Heapsort has this 2 n log n, so it's the worst in terms of number of comparisons, and Mergesort has this 1 times n log n, so it's the best in terms of number of comparisons. So really, none of these algorithms you could say is better than the others. They all have sort of advantages and disadvantages. And it really depends what you care more about. Is it the number of comparisons that you absolutely care about? If that's the case, then Mergesort is the best. But if you don't want to allocate extra arrays, a whole extra array, then Quicksort and Heapsort are the 2 options for you. And if you don't like randomization, if you don't like that the running time is only expected time, then you don't want to use Quicksort. So there's good reasons for choosing any of these 3 things. Okay. But one thing that you noticed here is, well, these all run in O of n log n time. Is there a faster algorithm? So is there an algorithm that runs in O of n time? Why not? And the answer to that question is no, there is no faster algorithm, but there's some conditions on that. And I'll show you that, why there's no faster algorithm. In fact, n log n is optimal for algorithms like these. So that's the fastest you can get. And then after I'm done showing you that there's no faster algorithm, I'll show you that there is a faster algorithm. And the apparent contradiction comes from the fact that the faster algorithm does something that these 3 algorithms don't. So it uses an operation that these 3 algorithms can't do. All right. So what do Quicksort, Heapsort, and Mergesort have in common? They're all comparison-based algorithms. So that means that if I examine the code for them, I will find things like if statements and while loops that have conditions in them. So they have Boolean conditions in them to say whether an if statement should execute or not, and whether the loop should continue or not. And those things are all based on the results of comparing 2 values in the array. So they will have statements of the form, is the element at this position in the array bigger than or smaller than the element at this other position in the array. Okay. So that means that they're what's called comparison-based algorithms. In particular, they don't look any more deeply at the values in the array than just comparing them. So to them, to these kinds of algorithms, the stuff in the array, whatever happens to be there, is just a black box. And you can take two of them and ask which one is bigger, but otherwise, other than that, you don't care what these black boxes contain. And that's nice because in Java, for example, that's what comparators let you do, right? The whole point of the comparator class in Java is that you define one of these things so that you can compare whatever objects you're interested in sorting. And once you do that, you can use any of these algorithms on those things without knowing anything more about the object. You just need a comparator. So that's what it means to be a comparison-based algorithm, is that the execution branches you make are based on the results of comparing elements in the array, pairs of elements. So I have a cat coming here. Okay, that makes them nice in general, but there's a price for that, and the price is that they can only sort, they can't sort faster than n log n time. In fact, they can't sort faster than roughly n log n comparisons. So what I'll argue now is that these kinds of algorithms, they have to take n log n time for some inputs. And the way to see that is the following. So let's just define an abstract concept, what I'll call a comparison tree. So a comparison tree is, it's a binary tree, and each internal node has two numbers associated with it. So these are indices into the array, I and j. And each leaf is a permutation of the indices 0 through n minus 1. And if you give me an array with some values in it, I can actually run the comparison tree on that array. So you start at the root, and so you set u equal to the root of this tree, and if u is not a leaf, you look at the two indices associated with this node, right? So this node u says, there's position I and position j, and you look in the array at those positions, I and j, and you compare these two things. And if I is, a at I is less than a at j, you go to the left subtree. Otherwise, you go to the right subtree. And then you repeat that. So now you're at a new node. That new node has a pair of indices, and you do the same thing. Okay. And we'll say that this tree sorts if for any input array you give me, it takes you to a leaf. And remember that I said that at each leaf there's a permutation of 0 through n, that if I look at that permutation and apply it to the array you gave me, then I get a sorted array. Okay, so that sounds very abstract. Let's look at an example. Here's a picture of such a comparison tree. So so this is a comparison tree, and it's a comparison tree for sorting arrays of length 3. So with indices 0, 1, and 2. And at the root of this tree, you look to see which is smaller, a at 0 or a at 1. If a at 0 is smaller, you go over here, and if a at 1 is smaller, you go over on the right side. Okay. So let's say that a at 0 was smaller. and now on this, now you look at A at 1 and A at 2, and you compare those and see which one is smaller. And you know, if A at 1 is smaller, you go over here to the left side, and now we're at a leaf. And the leaves of the comparison tree are supposed to have permutations associated with them, permutations of 0, 1, and 2. And in this case, this leaf, the permutation is 0, 1, 2. So let's think about that for a second. If we reach this leaf, so that means we checked which one was smaller, A at 0 or A at 1, and A at 0 was smaller. So we know that the smaller of A0 and A1 is A0. Then we checked A1 and A2, and we saw that A1 was smaller. And so that really means we know from checking the check at the root, we know that this is true. A at 0 is smaller than A at 1. And we know from the check here that A at 1 is smaller than A2. So if we reach this leaf, we know that the array is already sorted. A at 0 is smaller than A at 1, it's just smaller than A at 2. Okay? And you can actually check for each of the leaves in this tree that's what happens. So we'll check it for this leaf here. So if I go, if I reach this leaf, it's because I did this comparison and I saw A1 was smaller than A0. Okay, that's showing up right here. Now, it means I also did this comparison and I saw that A0 was smaller than A2, and that's showing up here. So the permutation that I would need to apply to A to sort it is I have to first put A1, it's the smallest thing, then I have to put A0, and then I have to put A2. Okay. And if you can check this for the other, the 4 other leaves of this tree, and you'll realize, yes, for each of those, the permutation that you see here correctly sorts the input that leads you there. So one thing you can see, this thing has 6 leaves. So why 6 leaves? Well, this is supposed to be a comparison tree that sorts arrays of length 3. And so that means that no matter what permutation you give me as input in my array of length 3, I have to sort it correctly. And the number of permutations of 3 elements is 3 factorial, and 3 factorial is 6. So this array, this comparison tree, if it's going to sort correctly, it has to have at least 6 leaves, because it has to be able to handle each of the 6 possible permutations of the input array. Okay, so that's how comparison trees work. But what does that have to do with sorting algorithms? Well, before we get there, here's what I basically just said. Every comparison tree that sorts every input of length n has at least n factorial leaves, right? Because if I give you 2 different permutations of, let's say, the integers 1 through n, because they're different permutations, to sort them, I have to rearrange them differently. I can't apply the same permutation won't sort both of them. So that means 2 different permutations have to take you to different leaves, which means the number of leaves have to be at least equal to the number of permutations, which is n factorial. Okay, so that's, and we saw that here. The number of leaves here is exactly 3 factorial, which is 6. And it couldn't be any smaller. Now, here's something useful about that that's bringing it closer to what we're talking about in terms of algorithms. So every comparison tree that sorts any input of length n has height at least n over 2 log n over 2. That's sort of an easy calculation that comes from this. If you have m leaves, if you're a tree with m leaves, then your height is at least log of m. But now we have m being n factorial, which means that the height is at least log of n factorial. And now you just fight with the log of n factorial to prove that it's bigger than something. And it's really easy to prove that it's bigger than n over 2 log n over 2. Okay, so that's why is that? Well, just look at the log of n factorial is log of n times n minus 1 times n minus 2 times n minus 3 and so on, all the way down to 1, which is the log of n plus the log of n minus 1 and so on, all the way down to 1. So throw away the last n over 2 terms. If you throw those away, you get something smaller, right? That's all this says. Just throw away the last n over 2 terms. Now each of those terms is bigger than log of n over 2. So if you set them all equal to log of n over 2, you get something smaller. But now there's n over 2 of them. So you get n over 2 log n over 2. And this is a really rough estimate. If you do this carefully at all, using what's called Stirling's approximation, you actually see that the truth is more like n log n minus a constant times n. Okay, so what do we know so far? We know that every comparison tree that sorts, that's able to sort all inputs of length n has to have height n log n, or n over 2 log n over 2, or this if you believe it. But what does that have to do with sorting algorithms? Well, so here's we'll skip that. That's just an example that I know immediately doesn't sort because it's trying to sort arrays of length 3, but it doesn't have enough leaves. Here's the leap. If you give me a sorting algorithm, like Mergesort, for example, then look at what that algorithm does when it's given an array of length n. And for now, let's say that it's a deterministic sorting algorithm. So that's like Heapsort or like Mergesort. So if I give it an array of length n, the algorithm runs for a little while, does whatever it's supposed to do, and then it eventually compares 2 elements in the input array. Okay, and before that, it did a bunch of stuff, but every time it runs, the first 2 elements that it compares, they're always going to be the same. Right? You give me an array of length n. If I run Mergesort before I do any comparisons, I will eventually compare 2 things. In fact, if you look really carefully, you'll see that the 2 things you compare are the first 2 elements of the array. If you trace through the recursion, and so there's a first comparison that happens, and it's always between the same 2 elements. So make that the root of the comparison tree. So Mergesort defines a comparison tree where that thing is the root. Now at that point, Mergesort makes a decision based on that comparison. And if the comparison turns out one way, the decision goes one way. If the comparison turns out the other way, it goes the other way. But so let's say that it compares items, array elements I and j, realizes that AI is less than AJ, does something, but now after that, for any input where I is less than J, the next comparison is going to be the same. So that's really means, okay, that defines the root of the comparison tree, and on one side, on the left side, I can recursively define the rest of the comparison tree, the left side of that comparison tree, and similarly on the right side. Okay, so it takes a bit of time to wrap your head around this, but really underneath every sorting algorithm, there's this comparison tree, and you can get it basically by just looking at where the algorithm makes decisions, and every time it makes a decision based on comparing two elements, that's a branch in your comparison tree. Okay. We never actually build these things explicitly, but we just know that they're there. And of course, if the algorithm is correct, then the comparison tree that it defines has to have n factorial leaves. Okay. And the height of that tree, well, that's just the number of comparisons, right? So a path in that tree, in the comparison tree, represents you running the algorithm and it doing a sequence of comparisons and then eventually finishing. So the algorithm finishes at a leaf of this tree, meaning that it's done sorting the array. So the height, the depth of that leaf, is how many comparisons the algorithm did to get there. And so the height is then, therefore, the worst case number of comparisons that the algorithm has to do to sort an input. And that does it, because we saw that a comparison tree that sorts all inputs of length n has height n log n, omega n log n, and therefore every algorithm, deterministic comparison-based sorting algorithm, must have a running time that is omega n log n. Okay? Because behind it, there's this underlying comparison tree that has height n log n, and the height of that tree corresponds to the worst case running time of your algorithm. And actually, so that handles deterministic algorithms. So that proves that Mergesort is the best it could be for a deterministic algorithm, and that Heapsort is also the best it could be, and its n log n running time is the best possible. And a slight variation on that theorem deals with randomized algorithms like Quicksort. In fact, all you need to do is look at a random permutation of the stronger theorem is that any algorithm, whether it's randomized or deterministic, if I give it a random permutation of the integers 1 through n, then its expected running time on that random permutation is at least n log n. Okay, so Mergesort is the best it can be, as are Quicksort and Heapsort. So they're optimal comparison-based algorithms. So that was the no part of the answer that said, when I said, can we make faster algorithms? The answer is no. We can't make faster comparison-based algorithms. But what about algorithms that don't do comparisons? What else could they do? So other than comparisons, what might they do? So let's think of an example. So an in-class problem, and we'll make it really easy. Suppose I want you to sort an array but I tell you in advance the array, even though it's long, it's of length n, it actually only contains 3 different values, 3 different integer values. And they are like, 1, 2, and 0. Okay, so it's an array, it's a big array of length n, but every entry in that array is either a 0, a 1, or a 2. Is there a way to sort that faster than n log n? Yeah, there is. I can just go through this array once and count how many zeros there are. 1, 2, 3, 4, 5, 6. So there's 6 zeros. And actually, I can just keep an auxiliary array that keeps track of how many zeros there are, how many ones there are, and how many twos there are. And by scanning this array, I start all of these counters at 0, and as I scan, each time I encounter a 1, I increase the value here. Each time I encounter 2, I increase the value here. Each time I encounter 0, I increase the value here. So with one scan through this array, I will know the number of zeros is 1, 2, 3, 4, 5, 6. The number of ones is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think if I got that right. And the number of twos is 1, 2, 3, 4, 5, 6, 7. And once I know that, now I know how to sort the array. What does the sorted array look like? Well, it's going to have 1, 2, 3, 4, 5, 6 zeros from there. It's going to have 11 ones. And it's going to have 7 twos. And that didn't take n log n time. All I had to do was scan the input array once and use that to fill out the values in this array. And once I have the values in this array, well then I can I know the sorted things now. This many copies of 0, this many copies of 1, and this many copies of 2. And I think you see that generalizes. Nothing special about 2 here. If I have entries 0, if the values in here are 0 to k minus 1, then all I need is a bigger array, an array that's big enough here to count those things. So if these take on a small number of different values, let's say k of them, then with this extra array, I can sort this in O of n time. And in fact, something really strange about that sorting algorithm is it didn't do any comparisons. So it never looked at 2 values in this input array and compared them. Instead, the branching that happened was actually done by taking these things and using them as array indices. So, right, I look up I take this data item, which is 1, and I use it as an index into this array, and then I increment the value there. I take this data item, which is 2, use it as an index in this array, and increment the value there. Okay. So it actually doesn't do any comparisons. These things, so it's not a comparison-based algorithm. It's instead using the data somehow directly to do branching, but it only works for this kind of integer data, so integers in the range 0 to k minus 1. So that seems limited, although maybe useful. But actually you can build something really nice with it. So first let's just be a little bit more careful about what we did here. So that idea that I just described on the board is captured by this counting sort algorithm. And this counting sort algorithm looks more complicated than what I just explained, and it is, but for a good reason. So it does what you expect. It creates an array of counters of length k. So that's that array in the middle in the picture on the board. And then it runs through the input array and goes to, at array position I. It uses that as an index into the counter array and increments the count there. So by the time this first for loop executes, we know for each value in 0 up to k minus 1, how many times that value appears in the input array. This next step here just takes a cumulative sum of those counters. So I'll just put that on the board to show what that means. That says, in fact, it takes a prefix sum. So this array here, this is the array of counters. It contained 6, 11, and 7. After that, it's going to contain 6. 6 plus 11 is 17, and 17 plus 7 is 24. What's the meaning of these numbers? Well, 6 is the index where the first one will appear, and 17 is the index where the first 2 will appear. Okay. So it just takes these frequencies and turns them actually into specific indexes where things should appear. And 24, another way to think of it, another way to think actually of both of these things is 6 is one more than the index of the last 0. 17 is one more than the index of the last 1, and 24 is one more than the index of the last 2. Then it allocates a new array. Back to the screen. It allocates a new array B where it's going to put the sorted data. And it goes through the original array A backwards and grabs the elements from A in reverse order and puts them just at the right place. Okay. So if we were going to look at that example on the board, it's going to go through this thing backwards. So starting here, so from the last one, and it's going to put it at exactly the right place. So how does it know where the last one is supposed to go? The last one is supposed to go right here just before the first 2. So that's where the first thing gets written. And if you look at the code, it decreases this thing so it doesn't point to there anymore. Now it points to there. And then it's going to put the last 0. Where should the last 0 go? Well, the last 0 should go right here. And then the second last 0, where should that go? Well, that should go right before the 0 we just placed. Okay. So that's how that works. And it might seem more complicated than necessary because we seem to have a simpler way of doing it, but it's helpful to keep in mind that, well, maybe the integers that we're sorting, that they're not just, it's not just some integer, but it's some integer and some data. And so when we do that, we really care about the difference between the first 0 and the second 0 and the third 0 because maybe they have different data associated with them. So So this is just a more careful way to do it, where we really are copying things from the array A, and if there was extra data associated with it, we would copy that extra data as well into the output array. And there's a nice property that this has, and it's because we just did it carefully, and you could see it in the example that I started to do, that it preserves the order of things. So the last one in the input array gets copied to the last one in the output array, and the last zero is the last zero in from the input array is also the last zero in the output array. Here's a picture of this thing in action. But that property is important. It's what's called stability. It means that if two things have the same value in the input, then they appear in the output in the same order that they were in the input. So it doesn't change their order if they have the same value. And that's going to be important in a second. So that's called the counting sort algorithm. And what's its running time? Well, it was just 2 loops over the input array, one loop to get all the counters set up, and another loop to write the output. And there were one loop in the counting array to sum up all of these things. So if the counting array has size k and the input array has size n, that's just O of n plus k time. So as long as k is smaller than n, that's great, right? I mean, that's linear time. All right. So that's nice, but not quite good enough. So when would this be useful? Well, if we think about Java, Java has ints. They're 32 bits, so that means they basically have so someone asked, wouldn't counting sort require you to already know the sorted order of the elements in the array? Example 0, 1, 2. No, counting sort works, it only works for integers, and I'll say integers 0 up to k. And we know, we know how to sort integers. They're just those things. So they're really just the integer values. There's no question about how to sort those. Okay, so if you think about Java ints, then, well, ints have 32 bits. That means they have about 4 billion possible values. So if we try and use counting sort directly on those, then we get a k that is 2 to the 32, 4 billion, which actually in Java there's a limit on the sizes of arrays. They're not allowed to be that big. And so that would say that if we try and use this in Java, k is always bigger than n. So k is 4 billion, and n is actually can't even be 4 billion. So it doesn't seem practical. But don't worry, we can do better. We can actually sort integers by using this multiple times. So integers have w bits. Let's say w is 32. We treat those integers as having d bits. So let's say d equals 8. So we treat them as a bunch of digits. So let's say d equals 8. So a 32-bit integer you can think of as really having 4 digits. Each one is 8 bits. So in that case, the values for the digits, the value k, is only 256. That's 2 to the 8. And now we do some, we'll have to do w over d passes of counting sort. And this is where we'll do something actually that surprises everybody when they see it. So first thing we'll do is we'll sort by the least significant digit, and then we'll sort by the second least significant digit, and then by the third least significant digit, and finally we finish up by sorting by the most significant digit. But the point now is, if you think of Java, W is 32. If I take D equals 8, that means I have to do 4 passes of counting sort only. And the size of my counting array is only 256. So that's pretty good. 256 is not particularly big. So the counting array is not big. As long as my array that I'm trying to sort is reasonably big, maybe it has size 10,000 or something, that this will still be fast. So like I said, it starts by sorting the least significant digits first and works up to the most significant digits. And the reason that this works really relies on the fact that counting sort is stable, which I explained. So if you have 2 equal values, then they will appear in the output in the same order that they appeared in the input. So this illustrates a sort of baby example where the numbers have 8 bits, and so W is 8, and we break this up into 4 digits, each of 2 bits. Okay. So here's the input, this sequence of numbers here. And in the first pass, all we do is look at the last 2 digits. Okay. So there's 4 possible values there, right? If we take a 2-bit number, that's 0, 1, or 3, and we sort by that. Okay. So that's what happens after the first stage of counting sort. So at the top are all the numbers that end in 2 zeros, then the numbers that end in 0, 1, then the numbers that end in 1, 0, and then the numbers that end in 1, 1. At the next pass, we look at the next 2 bits, and we sort by those. And this is where the magic kind of happens. When we do that, so yeah, we get all of the things where those 2 bits were 0 first. Here they are. Then all of the things where those 2 bits were 1 first. Then all the things where those bits were 1, 0, and then yeah, so 0, 1, 1, 0, and so on. But pay attention to what happened here, where all of these bits are 0. So we're sorting based on those 2 bits, and we had ties there. There were 3 of them which were all zeros. And how were those ties resolved? Well, those ties were resolved by the order in which they appeared in this array, because counting sort is stable. But this array was already sorted by the lower order digits. So here I have 0, 0, 0, 0 that showed up before 0, 0, 0, 1. And that's because in the previous step we had already sorted these things so that 0, 0 came before 0, 1. Okay. So this is really non-intuitive that you start by sorting with the least significant digits, but the fact that this thing is stable means that each time you do this, you have this thing perfectly sorted by its lowest order digits, and then all you have to do is do a stable sort on the remaining higher order digits. there will be ties in those higher order digits, and those ties will be resolved by the order in which these things appeared, which is according to the lower order digits. Okay. So, this slide is not perfect. So how long does this take? So it works for W-bit integers. You pick a value D, which is the number of bits that you want to put in your to make up a digit, and then the running time is 2 to the D, because you're going to have this counting array that's going to be in there. That's the size of your counting array. There's an n, and what's missing here, this whole thing should be multiplied by W divided by D. Okay, so in here D is 2, W is 8, and we had to do 1, 2, 3, 4 passes of counting sort. 8 divided by 2 passes of counting sort. And actually, if you work that out, that means that if you give me integers in the range 0 up to n to some power c, then the radix you use is n, so you set it so that 2 to the d is equal to n roughly, and you get something that runs in O of cn time. But practically speaking, so that's called radix sort. It treats this number as a base 2 to the d radix number. And practically, this is actually a really fast algorithm. So if I have 32-bit integers, it can sort them super fast. If I have 64-bit integers, same thing, right? A small array just of length 256 to do that counting means you can do 32-bit integers in 4 passes, and you can do 64-bit integers in 8 passes. And actually, it also means you can do floating point numbers, because the floating point, the IEEE floating point standard, was designed quite cleverly in that comparisons between numbers in IEEE floating point, they correspond to just interpreting the numbers as integers. So really, when it comes to sorting, that you can just treat floating point numbers as if they were integers, and sort according to that, and you'll get a correct answer, modulo maybe some strange cases where you might have infinities and minus infinities, and in floating point there's something called not a number, which may not work out, but that maybe doesn't make sense to be sorting things that are not numbers. Okay, yeah, so there's the summary. If you insist on doing comparisons, like in the whole Java world, then you're not going to do better than n log n time algorithms. On the other hand, if you assume something about your data, in particular, if you assume that it's integer data, then you can do better. You can basically get linear time algorithms as long as the integers aren't too big. Okay, and that is it for today. So you can ask me any questions if you like. Okay. So thanks for showing up, and I will see you again on Friday.